Okay, very good morning, all. Can you all hear me all right and uh, see the screen?
Yeah,
Yes,
good morning, Professor. Yeah, we can hear.
Very good. Okay, so as you all know, so today is this additional lecture that we have included for the program. So this will be on deep learning, again, continuing whatever we have been discussing so far, but applied to NLP. So NLP, natural language processing. So what I'll do is today is twofold. One is the first half of today's lecture. I will focus on NLP, and maybe if we need more time, maybe we'll also eat in some time from the second half as well. But cover the basics of NLP. NLP itself is like maybe a certification program by itself, which you can spend about 6 months to understand everything in detail. But what I'll do is try to spend some time understanding if you want to train an NLP model using deep learning, what are the preliminary things pre-processing that is typically done just to get an idea of what goes in before uh, we feed in something to a deep learning model. And then I will look at basically one particular very popular deep learning architecture, which is the transformer architecture, which is basically the one sitting in all the GPT, Llama, whatever OpenAI models that you see today. What I'll not be covering is like a lot of engineering that goes behind the screen and also post hoc, which is called as RAG, prompt engineering, etc. Those are things that I will not cover, but I will tell you what is the architecture of transformers, what is attention mechanism, self-attention mechanism, and basically dissect the transformer architecture, and then tell one of the transformer architectures, which one of the architectures which uses transformers to enable GPT, right? So with a like a small demo towards the end of today's lecture. What I also plan to do is spend some time to basically open up. We can have towards the second half of today's lecture, maybe, more interactive. So what I'll do is I will have to cover one particular thing that I promised earlier, that is batch normalization, which was part of the kind of the first lecture, but self-reading material. So I will, what I'll do is that is something that I will spend on um, uh, say 15-20 minutes on batch normalization. And then maybe what I'll do is I have a summary set of slides from all the 5 weeks that we have seen so far. So I will simply go through, just not, if there is no much interaction to keep us occupied, I'll go through the slides. But as and when, if you have any questions, I will moderate to let you unmute and ask. So the second half will be mostly Q&A and interactions, and kind of taking you through the the module itself. So I am assuming that the exam is already made available to you, right? So it is like a longer duration before which you can submit. That's my understanding. Today's lecture on NLP, as I already mentioned during lecture week 5, that this is an additional content that we have introduced. It will not be part of the grading or examination, right? So it is more because it is something that is getting so much attention. We thought it's worthwhile to include this additional model. Previously, the sixth lecture was mostly a revision week, but now we are reducing the revision week to introduce this module. That's how we have placed this. So this will not be included in the grading, but as I told, yeah, it is worthwhile to understand what is going on in these transformer architectures. Okay, so that's the plan for today. And so My understanding is that the exam deadline that you'll have to submit is 22nd. Is that correct? So it was already made available like
Yes,
two
it's
weeks
Yes.
back.
tomorrow due. Yep, it's due
Tomorrow,
tomorrow.
it is due tomorrow, right? So, yeah, you already had 2 weeks, but I see that one of you is requesting for, or at least, okay, is there a question about a deadline? So, if you need, maybe you can, uh, I don't know if it is like really needed at this point with 2 weeks already in line, but if you want like a few days extension before the start of the module, that should be okay. So, do you think you require, many of you require a few days extension, maybe after Christmas, before the start of the next module?
Just professor, that will be helpful.
Yes,
Yes,
Professor.
Professor. We all have some leave plans and travel plans, so that will help.
Yeah, but do you want to finish the exam and then enjoy the holidays, or you would like to do it during the holidays?
It's both good and bad. Bad
Yeah,
because
I mean, yeah. So in any case, I will check with the from my side. I don't see any concerns of extending it. Let me see. So we are 21 today, and yeah, I mean the downside is that if I extend it, then I'm sure like many of us are going on a year-end break, and then you'll be working on this. Uh,
Whoever does not want
so
extension, they can give the
tentatively,
exam now.
say that again.
Whoever does not want extension, they can take the
Yeah,
exam
yeah, of
before
course.
going
So I
for
mean, I
leave.
would, it's your decision when to submit. So tentatively, I will check if we can extend it by till 28th, if there are no other conflicts with the start of the next module and so on. So that should give some of you a bit of breathing room, but of course, it's up to you to manage your holidays and things at home, right? So that you're not making others at home unhappy. Okay, so let's get started. So NLP itself, maybe I already mentioned this during the introduction lecture, that NLP itself is not a new topic at all, right? It is as old as maybe the first days of artificial neural networks, right? So that artificial neural networks has also seen many waves. So beginning was mostly for image-based applications, but then NLP has been there for uh, many decades now. But with the advances in deep learning, uh, NLP also gained popularity. I remember like in the 90s, NLP was already kind of popular in automatic speech recognition systems, where the goal was, for example, to enable simple tasks like dictation or to enable basic tasks via voice command. So that basically involves like interpreting speech, understanding what we are speaking, and then converting it to another text or a command, right? So these were kind of rule-based query and response systems. But what we are trying to do of late is to learn these set of rules, right? So instead of having a set of propositions and many if-else clauses, we are now trying to figure out what is the underlying rule that would be best suited for a particular task at hand. And that has been the goal of NLP with AI in general. But with machine learning and deep learning, we're trying to learn these rules using artificial neural networks. And much of the tasks require some pre-processing to convert this language, understand what is a language, and then give it as an input to the deep learning model. So there is a lot of feature engineering going on. We will see what that is. And natural language could be spoken language, or it could be any language that we see as a part of text documents, right? So it could involve grammar and many other constructs that underlies a particular language. predominantly natural language processing has mainly been for English language, very few foreign languages as well, almost none for local languages, which like the Indian languages. But that is also kind of gaining attention because of the market around that region. So what we will do is this is what I plan to do. So we will do a bit of data pre-processing in the beginning and see how to what are the typical ways to embed a word. So while discussing RNNs, if you remember one of the examples when we're discussing RNNs, for example, I am Groot, right? So that was an example. And then if you remember that architecture, we gave every word a vector, right? Now, that's a number. So we have to now figure out what are the ways to convert a word to a vector. There are some obvious ways. There are more involved ways. We will see a couple of them. And then having this word embedding. So suppose I don't use any of these fancy new generation models. How do we do a simple task of text classification using multi-layer perceptron? So the model from lecture one. So that gives you a basic notion of, okay, building a simple NLP model. But then more advanced versions are to improve performance and also with a lot of engineering that goes into the MLP model itself and deviating basically from the usual multi-layer perceptron architecture, but more relying on how the language is generated, right? So how language or any spoken language, the sentences are formed, what should be used to predict, right? So in that sense, we will see what is transformer architecture. Before that, we require to understand what is an attention mechanism. And then we will look at a particular architecture called BERT and also introduce what is BART, which basically use transformer architectures. This is kind of a decoder only architecture, which is what you would see whenever you're looking for anything on ChatGPT or Gemini or Llama, right? So you might have heard about these architectures, but then whatever we will do essentially is wrapper around these architectures, right? So for example, you would use these models to do some kind of a prompt engineering, develop your own chatbots. So that's mostly engineering. There's nothing complicated to discuss, but if you want to understand prompt engineering or RAG, that's a kind of a lecture by itself, right? But that will not be doing today. And then after this, we'll go back to this lecture one and discuss what is batch normalization. That is one important thing. And then we will do the revision part. And that's the plan for today. So this will not be included again for the exam, right? So there'll not be, this is not part of the exam syllabus itself. Okay. uh, again, Geron's book that you have been seeing, that is this one here, has a chapter or a couple of chapters on NLP itself, right? So that is what I will be using. In addition to that, I'll be using this book by Soumya and other authors, which is more of a practical flavor of NLP. Right, so there are many books on NLPs, but this one is like without worrying too much about the underlying architecture, how to understand. So if you want to straight away use this book, you could basically start programming things. There are, of course, like many recent books which also talk about uh, uh, the say the RAG and then the recent developments. But okay, this is kind of giving you a flavor of both rule-based and then deep learning-based models. Okay, so I I I don't know if we have a mini project on NLP. I can check. Maybe we do have one. I can again, it will be an ungraded one just for you to play around. So maybe we will make it available, but for you to just play around with it. Gen AI and LLMs also, I will, yeah, I'll have to see what is the book that is along the flavor of Geron's, right? So it's Geron's book. If you have already, I hope many of you have already seen how Geron's book is. It is very simple, not intimidating for starters. And then you can basically, then once you know this, you can now pick up any of the newer generation papers or more involved books to understand more deeper. So this book on practical language, practical NLP is also along those lines. So it will give you a slow start, hands-on, let you feel what is going on, and then also has a lot of applications and business use cases like chat bot and other things. But so once you have this flavor, now you want to understand, maybe use a newer generation architecture so you can easily understand. So I'll be sampling sparsely sampling content from these two books for these slides. Okay, so you have already seen this picture on day one itself to basically understand within AI what are the technologies that are popular and how does NLP fit in, and what is the role of machine learning and deep learning in this context. So AI in general, you should understand it as a technology where you're trying to imbibe intelligence artificially, as the name indicates, into machines, where machines could be as simple as computers or any other equipment, right? So it could be a standalone equipment, but has some kind of a compute and compute power, storing power, and processing power, right? So that is what we would like to have. And the way that you can imbibe this intelligence, it could be in many ways, right? So for example, it could be simply a lot of rules that you put in and try to get one particular task done. Or it could be a broader context. You could have many tasks that could be done. And machine learning is more like a systematic approach where you use mathematics to model, right? Propose a model to solve a certain task, and you try to solve kind of an optimization problem, and that is what the learning means. So you're trying to learn the underlying parameters of the model to solve a particular task, and this is predominantly done again on a machine, right? So that is the goal. And deep learning, again, the broader idea is the same, that you would like to learn some parameters, but then instead of letting loose what type of models we can have, deep learning would basically make use of a particular architecture, a set of architectures which are derived from the perceptron model that we started, right? Artificial neuron and perceptron. Now, if you see this Venn diagram, natural language processing very well fits into AI because you're trying to process language, right? To understand the underlying grammar and process this language to again get some task done. Uh, but once you have this NLP task in mind, there are many ways to achieve it, right? So you can basically use again all these rules, right? So if you want to predict, you can put a set of rules without using any um, uh, tools that we have been seeing so far. So it could be simply how the language is formed. So we make it very specific to one particular language, and then you try to process it and generate maybe also like what we'll discuss next with the picture on the right. But instead of having a set of rule-based decisions, what we can also do is we can learn these rules. You can learn these rules using, for example, machine learning like logistic regression type models or linear regression type models, but also use deep learning. And today's lecture, the focus will be on this tiny little intersection where we are looking at deep learning because that's the focus of this module as well, to solve some of the NLP tasks. What are these typical NLP tasks? There are basically two main tasks whenever we are discussing with NLP at a broader context. If you take a step back and see what is the big picture behind NLP without getting into the details of how we do all this, there are two tasks. If you look at uh, these two boxes, there is something called as NLU, which is natural language understanding. And the second line that you see is natural language generation. Okay, so now think of any of this favorite automated agents that you would be using, for example, Alexa or Siri. You ask something and you expect back a response, right? So, for example, you will ask, what is the weather today? Or you would ask to call somebody, and then either you expect a response back. Okay, today's weather is blah blah blah. Maybe make it a bit more colorful and beautify the response. Good morning, and okay, the weather is bright today, etc. But you want that response to be meaningful, right? So you are asking a query. Okay, that has to be processed. It has to do some task, fetch what is the weather from maybe the database, and then it has to reproduce back, right? So reproduce back, which need not be necessarily reading something from a set of lookup table that you might have stored. That was basically what was done in the past. But now you have interesting ways of where the speech itself is very natural as humans would speak. It can basically generate not necessarily by looking at a set of preloaded messages. So you would like to generate a natural language response, which again should be grammatically okay, right? So it should not be uh, outside the language that you would expect, right? So it should be grammatically okay. It should have a natural flavor in the sense that as if humans are speaking and not some robot is repeating a set of text. So NLU and NLG are basically the two main tasks. Now, how do you do this is what we will try to understand, right? So, of course, we'll start not looking at the signal processing part of processing a signal from a microphone and then uh, uh, start converting into signals, and that signal then interpret into language. That is not what we will do today, but we'll assume that, okay, there is a document, and then that document has some collection of words. What next, right? And then once you have that, you can basically repeat the same process, for example, to generate the document itself. And then this particular part, like taking an input from a microphone or a camera to scan the images and then putting it back on a display or a speaker, that part, yeah, it's more or less pretty standard. There's nothing deep learning happening over there, but we will not focus on that part. So the starting point is like some text sentence or a paragraph is given to us. What next, right? That is what we will do. Okay, so that's basically at a very high level what NLP is about. But why is it getting so popular, right? So one particular reason why at least it is interesting to me is with coding, right? So you can basically, next to all the obvious applications like chatbot and other things that many of you already know, some of the things can be like, okay, it can be giving you a response that is kind of mundane, but now you want to start, like, for example, talking to a booking agent, like you book an air ticket and then you would like to make some changes. Instead of, yeah, you could basically start a conversation in WhatsApp, and then if it's not resolved, then you can ask it to connect it to some person behind the screen, right? So some of the initial pre-screening can already be done there. Those are kind of obvious tasks, and Alexa, Siri, needless to say, all of you know, it comes with a lot of negative ethical issues, like maybe the microphones are always on, camera is always on. You don't know who is listening to what. Many of you might have experienced that next to the cookie that are stored when you visit a particular web page. Now you also see that kind of cookies are also stored with whatever you speak, right? It's how the ethical part and the would shape up as we evolve. But some of the easy tasks that can be automated are, for example, coding, right? So coding, if you can, whatever you have been coding or whatever have been showing in the past 5 lectures with a simple command, okay, yeah, write a keras Python code. I mean, anybody, this is a free chat GPT that I use. So write a keras Python code for dense layers with NLP. So within a matter of seconds, this is generated, right? So what is the scientific message behind that, or that is up to us to use it in the way we like. Either we would like to learn this or need not learn, but then simply ask, and then, okay, you can use those codes. But also, for example, like no, there are many tools, mathematical tools, educational tools that are slowly being integrated with all these GPT models, which are seeing tons of data all over the internet, right? So this can be used for example, instructional and educational purposes as well, like a personalized tutor, but for some of the obvious tasks that we can also think of. So one disadvantage, obvious disadvantage compared to the simple machine learning, deep learning models that we have seen, we can train it with minimal resources that we have at hand, right? So, for example, to train the simple MLP, or even the not so simple, but something more meaningful, you can still do that with uh, a resource that is affordable, or at an individual level, or using free tools like Amazon or Colab type free servers that provide for a limited duration of time. So you can still play around, develop a decent model. But many of these recent deep learning models that are used for NLP, only the big players with millions of dollars, billions of dollars invested on these compute resources can only afford to train. So you cannot simply train a GPT, even like a GPT 3.5 or a 4.0 that is kind of recent, that models cannot be trained with the resources that at an individual level one can afford, right? So unless somebody has like a lot of money to play around with these things at an individual level, most of us cannot afford to train these models. So the market is naturally around now, okay, using those pre-trained models, but then to make it specific for a particular task at hand. Some of you might be developing chatbots, some of you might be using for some other medical tasks, and so on, right? So now there's wrappers that are built around that, which basically use those pre-trained models. So training, of course, is out of question for the models that uh, you mostly see, right, or hear about, right? And although some of the models that you don't even know what is, you can download the model, maybe pre-use the model, you don't even know how these are trained, right? So there is again like another direction that is has opened to make these models kind of open source, right? So some of them are kind of proprietary. They don't even let what that is, but you would like to see what is inside that model. You would like, rather than simply downloading the binary file and then plugging it and building a wrapper, you would like to understand, dissect what is going on around with it. So that's interesting development in the last couple of years, I would say, like bringing openness and transparency, considering ethical issues around all this, which should be which would kind of also be topics of interest in the next few years, right? So to have a policy around that, right? So we have policy and law around many things, but these things, what is ethical, that is not clear, right? So that is many of the countries are investing time around this. But anyway, so our premise is that NLP is useful, and then we'll try to understand what it is without getting into all this. And this is a simple timeline to see what is the time, how the development happened. So around these timelines, right? So 2013 to 2014, it was mostly artificial neural networks, MLPs, and RNNs that was used. Even before that, as I said, like there were um, um, uh, automatic speech recognition tools. Uh, I remember even in the 90s, like when I had this first desktop computer, it came with a Philips as a free goodie, an automatic speech recognition where you could basically dictate, etc. Right? So do some of very basic things which are kind of obvious today, but it has been around. But it really picked up popularity around this time when one could train RNNs, especially the LSTM and GRU models, for reasonable sized tasks. Of course, the limitations were immediately known, that it did not have some long range dependencies, and it did not have memory enough, even with the LSTM type architectures. But then one additional development that was also kind of not particularly related to the NLP task was this attention mechanism, right? So there was something called as a self-attention mechanism that was again for not necessarily for speech or image task, that was for an NLP, for an MLP output, or yeah, even for an RNN. How do I make it a bit more attentive to the input? We'll see what that is as we progress. But then the most recent developments were based on this attention mechanism, and the most popular paper that many of you might know is that attention is all you need, right? So then instead of going from sequence to sequence models, RNN based models, attention started playing a key role, and that led to the developments henceforth, right? So most of the newer models, many of them, I don't even know what is going on, right? So because of the lack of openness, but these are based on transformer architectures with a lot of engineering. Some of them make it openly available, transparent, many of them not. But you can always, they let you use the model at least. And the models itself have quite a large number of parameters. It is about usually billions of parameters. And using that model to an extent is also difficult, right? Unless you have like a pretty good server that can do inference on that, it is very high complexity. Okay. And the pre-training itself, the training again, it's twofold. One is that the data that it sees and the number of parameters it has, both of these make the task of training these models at an individual level almost out of reach for us. Okay, so with that introduction, let's take a look at what a typical NLP pipeline would look like. Okay, so again, it is a very high level introduction without getting into details of how it is being done. I only tell what is being done. So typically, whenever you think of an NLP task, again, the input being, say, a document, either a PDF file or an image file, or it could be obtained by crawling a web. So it has these particular steps. One is you have to acquire data, right? So acquire data is basically converting this PDF to a set of strings, etc. Or you build a script to build to crawl the web to read a PDF file. That is the obvious task that needs to be done. And then if you look at any text document, right? So for example, you would like to process this invoice. This is kind of a zero invoice, but But if that is an invoice, then it has like a lot of other things that is going on, right? So there's like a lot of white spaces, and then some information that might be processed differently than what is relevant. So you require a lot of text cleaning, right? And if it is kind of you're reading an HTML file, then it has many of this things that are related to HTML code, but what you might be actually interested in is the text that is underlying. So removing all this, right? So removing, say, the boxes around what text document you're seeing, or focusing on a particular aspect, right? So that is usually the text cleaning. So once you have the text, you have extracted from this document using some magic black box, you get this text. That text is, of course, not readily usable, right? So it's basically a collection of words. A collection of words. When you convert that to numbers directly, we will see later on, it might be meaningless. But we would like to preserve some context information, something about the grammar, and that is what we do in pre-processing. Okay, so once you have this pre-processed model, then you will have to do feature engineering. Feature engineering would basically mean you're adding some context information to that, some domain expertise to that, or you could simply start using a deep learning model at this particular stage, like what we will see in an example of using NLP for text classification. Once you generate the so-called word embedding. Okay, but before you generate word embedding, there is a sequence of steps that is typically performed that we will see as we progress. Okay, so that's basically the pipeline. And once you have this now, okay, so now you have a model which could be either a deep learning model or a machine learning model, and then deep learning could be anything, right? So MLP, RNN, transformers, or simple logistic regression model. And then what you would do is you would deploy that model, and deploy that model, or you would pass it through again like a text generator to put it back into a format that is easily understandable, right? So that's the generation part, and this keeps on going, right? So if you're processing word by word in a long sentence, you will have to do it kind of in a recursive manner. Okay, so now what is the issue with converting words as is into numbers? Okay, so now in order to understand this, let's take a look at these two set of words, two interesting words which lead to the same set of characters. You might already know this, like if you basically map every word to some number, you could use some kind of a lookup table. And one popular lookup table is the ASCII format, where each letter has a number, right? So it has a number associated with this. And now, if you look at this, two interesting things like New York Times and Monkey writes, if you look at the set of ASCII characters that are there, are basically the same, right? So you would basically have like 110, 101, and so on. And whenever you have an anagram, for instance, there are some interesting anagrams like carnivorous, coronavirus, Santa, Satan, teacher, cheater, and so on. They have the same set of ASCII characters. Now, if I start processing these numbers without taking the underlying meaning, then New York Times will become monkey writes, and what we will be processing would be something different. So a simple conversion of words or strings to numbers would not make much sense if your task is to process and give instructions based on the processed text, or to generate back the uh, context and the content information that we have, right? So that is problematic. Now, what are the typical ways to get around this, and how do we go ahead with this pre-processing task? That is what we will see next. Now, if you remember when we were discussing, are there any questions by the way so far? So far, I mean, it's only the high level introduction about pre-processing, just to make you aware, but in case there are questions, happy to take them. Okay, so now to give meaning to any sentence, have embed the context information in that sentence. When we extract the number representation of these, what is very important is to focus on the underlying language. If you remember, again, when we were discussing the CNN architecture, the CNN architecture was kind of developed keeping in mind how the natural images look, that the nearby pixels are correlated, and how the human vision perceives an image, right? So all this information was kind of incorporated through mathematical models and simplification of the NLP architectures. So for NLP also, the same thing is done in the sense that how we speak a particular language, right? So how we write a particular sentence in any language, right? So there is a set of rules which varies from language to language, and these are basically the what we call as grammar, right? So if you look at any language, typically it has how sounds, how the words are pronounced, right? So if you're doing any processing of speech, you need to focus on accents, and accents vary from who is speaking, and it is dependent on what language somebody is speaking. So these are basically the building blocks of any language, right? So it will have like something like root words, etc., phonemes or speech and sound, and then you basically have a collection of these words in a systematic way, which basically forms a grammar, right? So there's a syntax underlying that, like similar to a programming language. We have a set of rules. It might be logical, illogical, but those are the rules that any language would form, and then you form a sentence out of it. Now, the sentence itself also has an underlying context, right? So, for example, if you look at these last sentence here, man bit dog versus dog bit man, right? So now there is nothing wrong grammatically in the two sentences, right? So man bit dog, dog bit man, both of them are English grammar wise okay. Okay, now, but there is an underlying context, so that is important. Maybe there is sentences before that which would make dog bit man maybe less likely than man bit dog, right? So that context information is important, and some of them are commonsensical, right? So if you don't see any context before that, right? So for why did this man bite this dog, there should be some information available, but without that, both of them are grammatically okay. But without anything, common sense would say that very likely the first one uh, might not occur, right? So this is how you can include context information, and that context information would mean that I need to now also know what was happening before, rather than simply converting each of these sentences into ASCII characters. So the pre-processing part itself is quite involved in NLP. What we will not focus on is this part, right? So speech to text, etc., is not something that we focus on, but I will spend some time on understanding what is this tokenization, how to do word embedding, and within that we will also see what is the POS tagging, which is part of speech tagging, right? So that basically is kind of the basic building block of generating these vectors that we will use as an input to the deep learning model. So the tokenization itself, right? So if you think about whenever you see a sentence, it has two particular things. It can have punctuation marks. It can have spaces. You will have to get rid of all this. And a process of the pre-processing step is the following. You have something called as a tokenization, an n-gram tokenization, where you see this following word, right? So the mouse ran up the clock. The mouse ran up the clock. You can represent it as tokens, where you can think of representing each word as a token, where the words are the mouse ran up clock. So you basically extract these words as individual tokens. In this particular case, you have 5 tokens, or you can do a 2-gram tokenization to represent a set of 2 words as tokens. Okay, then subsequently we'll see what happens with this. But in order to do this, you might have to consider the underlying grammar into account. For example, okay, the mouse ran up the clock. There might be removal of punctuation that you will have to do. You would not want to represent, in many cases, words with different casings as different numbers. Okay, how do we come to that number? Okay, so the eventual goal is like I will have to represent this in terms of some vector that preserves meaning in the word as well as the sentence. That is our eventual goal. But before we do that, do we have to, for example, I can have like a D with a capital T or a lowercase t. That distinction do we need to preserve, or can I get rid of that, right? So that is what is one of the pre-processing that is done. And for example, we have this word here, ran, run, running. All these have kind of a root word, which is all this stemming and lemmatization is about, right? So you would like to now, when you're processing, you might want to remove certain prefixes which might change meaning if you don't do it appropriately. For example, yeah, you see that formality, and so there are some root words, but adjustable and adjust, or you might want to remove those suffixes and prefixes. But also you would like to preserve this lemma behind the sentence, like what I was telling, ran, run, etc. They have to be the same representations. So in pre-processing, you have these particular steps that is typically done before you represent. And once you have done all this, then comes the tokenization. Typically, you would do something called as an n-gram tokenization, where n is some number. So the pre-processing is done before, and that's not necessarily stored, right? So you basically tell what type of pre-processings that you need to do, right? So these are standard things, nothing changes. If you say English, then English has a set of lemmas and stem words. So you want to remove that, you don't want to remove that. That's a decision that one would make. You want to preserve the casing, is a case sensitive or not? That is a decision that you make, right? So these are some basic things that is kind of repetitive if we know what language we are processing. Once you do that, again, the choice that you need to make is, suppose this is the sentence that we are looking at, and you have done all these pre-processing, such as removal of punctuation, etc. Now, the first starting point is this tokenization. The n-gram tokenization, typically a 1 gram or a 2 gram, that is depending on how much you want to squeeze in the size of your embeddings, right? So do you want to represent like 2 words with 1 vector or 1 word with 1 vector each? So it is basically separating, extracting words. This is not at word embedding, right? So now this goes as an input to the word embedding, okay? Now, if you look at any of the libraries like Spacey, you basically have these uh, preloaded libraries which can do all these things for you, right? So all you need to do is you need to basically import this library, and with a simple command you basically get, if you feed in this sentence, you would get back the tokens as you request. The other thing, as I was mentioning, is as a part of this sentence processing, is this is not at word embedding, right? As I already mentioned. So suppose if this is your input, then you might want to, for example, remove these punctuation marks. Okay, and then you would also want to do something known as a part of speech tagging, right? So what that basically means is, if you want to include a context information, you would like to do introduce, okay, what type of so this is like in the top, okay, bottom is a sentence. This is the tokenization with lemmatization, for instance, where you replace wrote with write, remove the punctuation, directed is direct, and remains, and compose the same, and so on, right? So you remove the plural, etc. But this is the tokens that you are extracting, okay, with a 1 gram token, for instance. In addition to that, once you have once you have extracted this token, each token might be having additional information. For example, you would like to say that this is a verb, right? So wrote, direct, etc. So or it should be like, okay, it's an article, etc. That you would like to also tell to give additional information, right? So in terms of a context. So this is called as POS tagging. You can do that. You can ignore that. But anyway, this is like a step in uh, uh, the pre-processing step. So the advantage with say 2 gram or multi-gram more than 1 gram tokenization is that if you have long sentences, if you see now, what I could do is I could basically represent the adjacent words with a vector, right? So now compared to this versus this, what you basically now try to embed and give meaning is who ran. And the second case with 2 gram, it is clear that it is mouse ran, right? So you're kind of using a sliding window where that already takes into account what is the context information, right? So that is the advantage with 2 gram versus n-gram, but also that means that you are compressing more words into the same length vector, right? So these are the typical pros and cons of using a 2 gram or a 3 gram tokenization versus 1 gram tokenization. The next step is, once you're done with tokenization, for example, a 1 or a 2 gram tokenization, you decide which one to do, is now to assign index to each of these tokens. Okay, so for example, if you see here, the mouse ran up the clock. The second thing, it's not just one sentence that we will process, right? You will process a sequence of sentences, which basically forms the text that we are looking at. Now, when we are processing that, there'll be certain repetitions, right? Repetitions, for example, even in the first sentence, the article the appears 2 times. So you would not want to assign a new index to the second the that appears, right? So although if you simply start counting, because again, the goal is that I would like to preserve that context information, but also assign a vector. Now, if there are repeating words, right? So if the collection of sentences that we have is mouse ran up the clock and the mouse ran down the clock, clearly ran is appearing twice, mouse is appearing many times, clock is appearing many times. Only thing that would change is the up and down here, right? So up and down means I basically need to assign very few indices compared to the number of words that appear in the sentence. Okay, so for example, like, yeah, you have this text as mouse ran up the clock and mouse ran down the clock. That is the then sentence that we are dealing with. So the index associated to each of that, it is a number, right? So now, depending on what 1 gram or 2 gram tokenization in this particular case, I have assigned index for both. You see that ran would be only once. Up, yeah, maybe the mouse ran. So the mouse ran up the clock and mouse ran down the clock. So ran up the and the clock. So each of them gets a different index that is assigned. Okay. Maybe that's a bit more clear here. The tokenizer itself, you don't have to do everything from scratch. Keras has a nice tokenizer. For example, if you want to use this tokenizer, you would want to use this pre-processing library. So again, if the sentence is mouse went up the clock, you can limit your tokenizer to tell how many words do you expect in your language, right? So for example, in the database that you're looking at, maybe 100 indices assigned to each of these numbers are fine. So for example, the mouse went up the clock, right? So now if you see that the second D does not have any additional index, okay? Now it could be that you would like to filter out certain special characters that is not required. That is also what is typically done. You would not want to assign an index to these special characters. And you want to keep everything lowercase. You want to have an out of vocabulary token. For example, uh, oftentimes you train on a certain set of words, but then that's not exhaustive, right? You can encounter uh, words that are outside the vocabulary. So in that case, every time I see a word that is outside my vocabulary, I would like to reserve a certain index for that, right? So that is what this OOV token tells, out of vocabulary token. But anyway, so now going back to what we were discussing. So I use 100 indices. This is not a word embedding, but this is a sequence of steps that I'm taking you through. So these are the sentences. The mouse went up the clock struck 1, the mouse went up the clock again, right? So with an exclamation. So you're basically ignoring the exclamation mark, and then the clock mouse went up. Yeah, all these have indices, right? So it is basically building upon what you already had in the dictionary before, right? So uh, so that is an example of a tokenizer. Yes, so the num words basically tells what is the size of your dictionary, right? So suppose, yeah, right now you have indices from 1 to 5, but then you can keep on extending that language, right? So every next sentence, you would start assigning unique words with numbers after doing all this pre-processing. And then the limit is 100. Now, if after 100, then it will do something crazy, right? So that's what you would store your memory as. So as I already was mentioning, suppose you don't know if your initial dictionary that you set up is exhaustive. So you will reserve also a token for out of vocabulary. So for example, you don't know what to do. So in case like, okay, you process the next sentence, next to these sentences, you will also reserve one particular token for out of vocabulary. Okay. And sometimes it is useful to not just treat words as or a set of sentences as a collection of words, but to treat them as it is, right? So as a sentence itself, and each sentence need not necessarily have the same number of words. Okay, so you would have a sentence with 5 words, 4 words, etc. But what you would like to ideally have is to have all the vectors with the collection of indices the same number. So in that case, what you would also do is you would say that pad my sentences which are shorter so that they have all the same then. So then you do a 0 padding before or after that is again a command that you would see, right? So in this particular case, for each of these sentences, we have a unique number assigned to the words that appear in that sentence. And then since the sentences are of different word counts, so for example, this has the first sentence is 6, but the second one is 4. So you would limit the sentence to be of say length 5 or 6, and then the padding would happen. Okay, so this is basically the very first step of processing a natural language. As you can see, what is also apparent is this is relying so much on English, right? So English as a language for processing. If you want to do the same for Kannada or Hindi or Telugu, you will not be able to use these as it is, right? So you would feed in a Telugu text, doesn't necessarily work the way it works. And that is also one of the reasons why your GPT might not be so useful when you are doing something in Hindi, for instance, right? So that's something that the other reason is that the data that all these models have seen are predominantly English-based databases. Okay, so yeah, that's again about tokenizer, but a little detail that you could do like a pre or a post padding, like you would like to add zeros before or after, but I guess you get the basic idea. So you have now these tokens which are assigned indices. Now, how do I give meaning to these tokens? And that is what we essentially do with word embedding, right? So there is no reason to do post or pre-padding, but it's just a convention that you follow, right? So you would just say that if I see any words that are of different, I mean, sentences with different word counts, you basically process the first few zeros, right? That's just a convention that you would follow. Now, you have these indices assigned to words. So these are numbers. Now, computers can only understand numbers. That is what is your starting point, right? So the whole point of the discussion on the past 5 to 6 slides is to basically get a number out of a word, right? There are many ways to do that. The typical practice is the one that I discussed so far, right? So making abstraction of many things, but you basically have a number for each of these words. Now, there are two ways. One is a stupid way, the other one is a slightly involved way, is to directly use one hot encoding for each of these sentences that you see. For example, we are having these 4 sentences: man bites dog, dog bites man, and so on. So you have these numbers assigned to these words that appear in these in this document, which has 4 sentences for you. Assign a one hot vector for each of the words. The advantage is that you have a unique representation for with one hot encoding, but the negative is that the size goes really proportional to the number of words in your vocabulary. And you just have this set of encodings, but it does not differentiate necessarily between D1 and D2, right? So D2 is also having a similar encoding. So D4 also has a similar encoding, but it does not distinguish, right? For example, dog bites man and dog bites a woman, right? So yeah, you expect that, okay, these two embeddings should be somewhat close by in the embedding space, but doing a one hot encoding doesn't necessarily give you that. So that's another disadvantage. So this is one stupid way of generating I would, yeah, may not be stupid is a harsh word, but this is a way of generating an embedding, right? Why is it less useful? Because it does not carry that similarity information between two sentences that we desire. The other method of generating word generating word embeddings is the so-called bag of words, right? So bag of words, as we see here, it basically counts the number of times a word appears in that document, right? So for example, D1, okay, so you basically look at D appears, say for example, how many times, byte appears how many times, and so on, right? So that is the bag of word embedding. It is also BOW, which is also a popular embedding. And OOV will also be a particular index. So for example, man bites a cat. I mean, sorry, a dog bites a cat. If that is there, then cat might not have an index. So now as soon as it encounters this dog bites a cat, that will be given an OOV index. Okay. So OOV index, again, instead of like having like say 1, 2, 3, you will have 1, 2 index for OOV, let's say it is 7. Now you do a one hot encoding or a bag of word encoding for this 1 to 7. So OOV, whenever you see a new word that you have not encountered before in your dictionary, you treat it as an out of vocabulary word. And out of vocabulary has an index, right? So it can have multiple indices as well, right? Because if your training data is limited and what you expect uh, after deployment is much more larger than your initial dictionary, then you might want to reserve more indices for out of vocabulary, right? So not just one, but then you might want to reserve like a richer set of indices. So then every time you get a new word, it randomly allocates a new index just to differentiate between a cat, maybe a monkey, and so on, right? So that doesn't appear in this dictionary, but you don't want to assign cat and monkey the same number. So you can basically have more indices for out of vocabulary as well, right? Okay. So these are typical ways, but so once you have this kind of an encoding with you, now you are in business, right? Business in train to set up your first uh, uh, model to achieve a particular task, right? So just to put this into perspective, you have tokenization, POS stacking, and then you will have an end of token to say that the sentence is ending now. And then you would like to perform some inference on this, right? So inference could be like sentiment classification, like what we were discussing with RNNs. And the way you would do that now is you will have a document pre-process. You would get an embedding. What is that embedding? We will see that. So we already saw two embeddings, which is bag of words or one hot encoding that goes as an input. And then you train a deep learning model, which is basically an NLP after you do all this to achieve one of these particular tasks, right? So sentiment classification, you would like to say, is it like the man bites a dog, right? So what is the sentiment associated with that? You could basically give that as an input, train for certain loss function, which basically enables us to learn these models, the model parameters. So that is what you would do in deep learning. In classical NLP, what you are doing is you are now looking at all this indices that you have extracted, right? So after tokenization, etc. Now you start parsing these through a set of rules instead of learning set of parameters based on a certain loss function. You start parsing these rules, right? So for example, like, okay, this is what you expect when a sentence has a bad sentiment, negative sentiment, or a positive sentiment. That is through rules. And then though, so it would basically count like, okay, how many times there's negative words, right? So you can form a set of if else conditions. That is what you would do to still process these text documents, but with a classical NLP. Here, as we saw before, you're not using any feature extraction to extract further from that set of embeddings, but then you would basically use a deep neural net to extract and do interference, extract features and do interference as well. The loss function is again the usual loss function, right? So for example, you have set of examples. Now the examples are say D1, D2, D3, and so on, right? The set of sentences which have a representation in terms of these words. But then you would like to do a sentiment classification, for example, it's a positive and a negative sentiment. So each of these sentences in the database has a set of labels. So y1 has 1, y2 has 0, y3 has 0, and so on. So what you're basically getting at the output for each of this example is an estimate of this label. And then the loss function is as usual before, so yi hat. Okay. So for example, if it's a positive negative sentiment, you extract. The only difference is that so far we were assuming that the numbers were readily given to you. The difference is, or the discussion so far is, how do we get those numbers, right? So I've shown you two ways of getting those numbers when dealing with a text document. And the loss function, so once you have the input, nothing else changes, right? So if it is like um, uh, you would like to do sentiment, or you'd like to do a classification task, if you're using a translation, we'll see a bit more about that as we progress. But there's a loss function associated to that, and the loss function comes from the training data. Shibani?
Yeah. One query, okay. So when you are using the bigger word or the one hot encoder, for example, dog beats man, right? We have three words here. The combination of all the words it will take as an input, and based on that, it will predict what is the a sentence. Is it like that, or combination?
So
If I take here, it is 3 by 2 combination, right? All the words it will come up, which is nothing but it can form for the D1, it can form 6 different combinations or 5 different combinations. All that it will convert that indexes, and then it will takes that as a input. This is how it is, or how system knows that I'll not take 7 or 6, I'll only take 1 or 2 as a input, or it takes everything. That is what I have the doubt.
yeah, so far what we have done is we have a mechanism to assign numbers to each of these words,
Yeah.
and two simple ways to further convert these numbers to vectors.
Okay.
Okay, so that is all we have done so far. And the vector that you would use, it can be fed into as an input to the MLP or deep learning model. Now, we have not discussed whether this embedding is good or what is actually required for us. But so in this particular case, so you will have like 4 examples. Each example has 3 words, right? Or you can have like maybe with a padding, you can have like one extra
Extra.
word. So to match the size of the sentences that you expect. The task could be that, okay, you would like to predict what comes next or do sentiment. So we'll come discuss all that later. But the point is that now there is a mechanism to convert that into a vector that you can feed as an input to any machine learning model. And
Okay.
here, what you might obviously already recognize is that there is no I mean, it's a set of words. Maybe the deep learning model will extract, but clearly we are not giving any context information, what comes before, what comes next. These
Yeah.
are simply 4 examples. And
Yeah.
a way to convert words into numbers. That is
Okay.
all we have seen. So is this a good way? No. We will
Okay.
see what is a better way.
Yeah, here what my doubt is, right?
Hmm.
When the bag of words with the D1 is nothing but 111000,
Hmm.
does that mean since we have dog beats man, so dog is index is 1 and beats is 2 and men is 3, so it is becoming the dog the from right to left if I read, because we always read from right to left, right? If I read from left to right, here 111 represents the dog appears 1, bits is to appears 1 time, man is appears 1 time, then 000 is rest of the indexes will be 0 occurrence. Is
Yeah,
that
so
represents?
the bag of words,
Yeah.
okay, so yeah, you okay, the question is like how bag of words we get here. So
Exactly. Yeah.
yeah, so
Yeah.
for example, in our dictionary, we have six words. So if you look at any Oxford dictionary, it might have thousands of words.
Okay.
But I'm not processing the entire English language, but
Hmm.
my universe is this four sentences.
Hmm.
And this four sentences has only six words. So my
Yeah.
dictionary is very simple, six words. Now, D1 would basically count how many times the words in the six dictionaries appear in which place. For example, dog,
Okay.
first word in the dictionary. Bite is a second word in the dictionary, so it has a
Hmm.
one. So,
Hmm.
for example, if the sentence was like dog bites man,
Hmm.
man bites dog. So D1 and D2 are clubbed. Then
Yeah.
the first entry would be two. The second
Okay.
entry would be two. And the third entry would be man, that is also two. And the remaining words, remaining indices will be 0, 0 because I did not encounter, for example, meat,
Those words.
food,
Yeah.
and
Meat,
yeah,
food,
that is
and
how you
eats.
would
Yeah.
generate bag of words. So
Okay.
yeah, that is what I also meant as a disadvantage. Now, the bag of words, if you look at this, now if my dictionary has 10,000 words,
Hmm.
irrespective of how big the sentences are,
You have to make the
the
10,000, yeah,
yeah,
entries. Yeah.
D1 will always
Yeah.
be 10,000 words.
10,000. Yeah.
Right? So that is the
Yeah.
disadvantage. But that is again another way, one of the early popular ways of representing a sentence uh, with a vector input.
Okay. Okay.
Yeah, there are other ways, right? So this is kind of doing like a frequency count, like what Srivatsa is referring to. So you're basically counting the frequencies, right? How frequent is the word appearing in that sentence, right? So that is the other name. So what I just mentioned is the way of counting the words based on frequency, right?
Okay.
Yeah.
Thanks, Professor. Yeah.
Yeah. Tripti?
Hi, good morning, Professor. I have a generic query. I put it in the chat also. So these pre-processing steps in the libraries and dictionaries that we are mentioning here, if you want to reuse it, you mentioned a library also, Space C or something like that. So is that library include the pre-processing steps that could be common for different models? Right? I don't
Yeah,
want
yeah.
to do it again and again, right?
Hmm.
Or maybe a
Yeah,
version
no,
of
yeah, I
it,
mean,
and
yeah,
I want to do it.
Spacey is one such library, but there are many such libraries. Yeah, I mean, no, yeah, I mean, yeah, you would not even go through what is going on, right? So you basically feed in a text and then
Hmm.
you have to give in certain arguments, like you require these filters on certain characters, and you need to include outer vocabulary, etc. So then all you see is this numbers that you get.
Okay. And
And
we can
even like, yeah, even like what we will see next, there is a tokenizer, and then you would basically also give as a parameter what type of an embedding you would like. You would like a one hot
Okay.
embedding or a bag of words. So the
Okay.
output is basically this vector that you can directly feed into a network model.
Okay.
And there is uh, uh, nothing that would change uh, uh, depending on what input you give, except for the output. But the way these inputs are processed, starting from the document level, is very similar when we are dealing with English.
Okay. Thank you so much.
Yeah. So here, so I mean, you would start processing related to Gaurav's question. So you would start processing sequences. You would not simply, as I explained, like do a sequence or a sentiment analysis for D1 itself, right? So you could do that, but we know why it is problematic, right? Because you don't know how long is your sentence. You would not want to reserve the number of parameters of your neural network based on the size of the sentence, right? So you would use the RNN model or something that is kind of sequentially processing. This is just to illustrate that, okay, for example, if I'm using a bag of word with 1,000 or 10,000 length vector, it is a possibility, but if your dictionary is like a million, then you are using million neurons in the input. So you would not do that, but like the way I'm telling you, but you would use kind of an RNN where you're processing one word at a time and so on. So this is typically whatever tasks that you have, whenever you see a certain task in mind, it is always supervised. Okay. So unsupervised would basically mean that, okay, now you would like to see see a general way to obtain embeddings irrespective of a task at hand, right? So even the GPT models that you see are trained on two particular tasks. We will go to that as we progress, but those are again solved on two important tasks, right? So we will see what that is. So unsupervised, you should imagine that, okay, you're doing some analysis of how the embeddings are there, etc. Right? So this is always supervised. So maybe we'll do this and then pause for the break. So far, there is no meaning from that would discriminate D1 and D4 sentences. Okay. But naturally, when I'm this vector encodings that we had using bag of words or one hot encoding, D1 and D2 might be very close to each other. For example, dog bites a man, dog bites, say, an old man, right? So now, whenever you're generating vectors out of these, you would like to have some similarity between these two vectors, which the two methods that I mentioned before is not giving you. And that is what is illustrated here. What is desirable of this word embedding that we generate. And some of the things that take into account, like this word to vec or glove, etc., are based on this basic idea. Again, there are like pre-select arguments that you should basically give to generate such embeddings. But for example, imagine that I'm embedding a vector into, say, this two-dimensional space. Then I basically need to think of two things, right? So if I'm doing, say, embedding of these four words in the two-dimensional space, if I have a good and a bad word, if I want to convert this, they should be as far away as possible because they mean opposites, right? But then not bad. If I want to encode that into a vector, not bad is closer to good, which means that the vector that I would basically assign to not bad is more aligned to good than bad. Okay, so that's the basic idea behind getting representations that are meaningful. Similarly, other examples or how this is typically done is basically through an iterative method, like that is what is illustrated here. So you would start with random vector assignments, and then you would pass that through some black box where eventually after a few iterations, as indicated by this dotted lines, would converge to embeddings that are meaningful. For example, near ocean and near bay, right? So language wise, they mean the same. So you do some processing so that the embeddings are close by, and ocean and island, inland, and less than 1 hour from ocean. So you see that embedding space has some meaning. So now if you want to classify, right, so what is land and what is ocean, so you basically put some classifier around this, right? So that's the basic idea. So again, the other way to look at this is, so for example, although there's a lot of bias here in this way of assignment, which is also one of the very important topics that people are pursuing within AI, policy-wise as well as ethical-wise, is to include fairness. And that is basically also nothing wrong with the method itself, but that is basically telling what the data is about, right? For example, it's common to interpret doctor as a man or nurse as a woman. So we know all these examples, but no problem with the network models, but that is how the data is. For example, like, okay, a simple prediction task that you would like to think is the following, right? So you have embeddings for different three different objects here: king, man, woman, and queen, right? So now, if you want to do a simple match the following task, right? So you have embeddings for king, you have embeddings for man, you have embeddings for women. And now you would like to predict what is the embedding for queen, right? So in that case, you can use all these three embeddings that you have for the king, man, and women and try to predict the embedding for the queen. And then you can do a simple rule-based heuristic like a translation, king minus man plus woman, that is going to give you this particular embedding, which is very close. So now if you have that embedding with you, you can do many downstream tasks. So this is the basic idea behind generating how embedding should look like. Maybe you would like to include fairness in terms of gender um, and the geography into account, etc. Right? So the demography into account and so on. But those are things that are more involved in terms of development. So now to generate such embeddings, you can basically again use scarers where this is what you would do, right? So you would basically have a vocabulary to start with, and then you would say like, okay, I require two indices for out of vocabulary, and the embedding dimension is two. So that means that each word should be assigned a two-dimensional vector. So you do all this tokenization, etc. And then you simply call this, instead of a dense layer, you would call an embedding layer, which is basically learning these embeddings based on the task at hand. For example, if the task at hand is to predict the embedding for queen, right? Then these embeddings that you would learn after during this iterative process would be for that particular task. So it is a particular block that you would include in your end-to-end task, right? So which means that either you can use some offline methods to generate embeddings like bag of words, glove, or one-hot encoding, or introduce an embedding layer like what I was showing, so that these indices are converted to more meaningful embeddings during the training process, right? So you basically add this particular layer telling what is the dimension of the embedding, etc. You have some initial embeddings, which are random initialization. But as the training progresses, if you look at, take a dump of this embedding layer and see what is the embeddings that it assigns to each of these words in your vocabulary, that would have some meaning based on the task at hand. Yeah, maybe what we'll do is if you have any questions at this point, I can take. Otherwise, we'll pause for a break and resume back maybe at 11:05 or so to continue further. So I don't see questions at this point. So we'll pause for a break and resume back with a simple illustration of an NLP task, and then continue further towards transformers and other things. Okay, so let's get started. So recall that before the break, we were looking at how to generate tokens, assign IDs, and generate embeddings using a Keras model for sentences, right? So that we extract from the document. So what we'll do now is look at a particular example and then proceed towards transformers, right? So it's the plan for the remaining remainder of today's lecture, and then backpropagation and some questions around the module. So this is a simple example, again, related to sentiment classification, which is a very important problem these days, especially with social media. To process text which appear as tweets, for example, to detect fake news. Suppose, okay, somebody tweets that, okay, there's like too much rain happening in Bangalore now and people are submerged, right? So it could be a real news, it could be a fake news, or it could be some sarcastic post that is around, or it could be a post that is coming resurfacing from maybe 10 years ago, right? So these are important challenges, especially with the social media, especially, for example, like, okay, if there's a bomb threat, is it like serious to be taken seriously, or is it sarcastic, etc., right? So it's an important problem, and many security agencies that I know of in the country, as well as outside India, they are working on these. So this is like related to that, but kind of a toy example setup, where you would like to predict whether it is a fake or the post is some kind of sarcastic, right? So now what you do, you basically have a data that is from the web. You crawl the web, and then uh, it contains labels on the training data, and the article link, which contains the text, and then the headline of the article. That's basically the data that we have, and we have many examples of this. So now what you would typically do is to set up, maybe we'll focus on the architecture, which is kind of obvious, should be obvious by now, is that, okay, after you do the processing that we discussed so far, the tokenizer and padding, etc., you set up an embedding layer. So here what you're doing is, instead of having a pre-computed embedding that works for irrespective of a particular task, what you're basically doing is, for this task of detecting whether the news is fake or the sentence is fake or sarcastic, you are learning embeddings that are for this particular task, right? So bag of words or the one hot encoding, that works for anything, right? So it's not designed for this particular task, but the embedding layer that we include is for this particular task. So it is fine-tuning the vectors in that would generate in the embedding space based on this particular task. So what we'll do is we will set up an embedding layer and a bunch of dense layers, and start training with a binary cross entropy, because we're doing a classification problem. Select an optimizer and then the display measure, right? So now if you look at the parameters, etc., these are the number of parameters that we get, that we see here. This is again from the model summary, and you start running this, you would see that, okay, the accuracy is about 81% on validation data, right? So although it is hitting about 99% on the test data, validation is more representative of what to expect during the test phase as well, right? So that's a simple example how you can use for this crawling of web page based example, and a simple MLP that we have already seen, right, for doing this classification problem. But oftentimes we are not limited to classification problems from text, right? You would also like to do prediction, like sequence modeling. Now the question is how to do that, right? So this is again like an illustration of how to, what happens for that particular thing, right? So the weather today is bright and sunny, whether it is sarcastic or granny starting to fear spiders in the garden might be real. So these are some sentences that are coming from the database, but then we can predict based on the model that we have trained. Okay. So you can also use any other models that we have seen in the same context, right? You can use basically a 1D CNN instead of an MLP, or you could also use RNN in the same context to start processing each word at a time. But I guess you get the essence of how you can use the starting from the text documents or crawling the web. What are the steps that need to be done to start doing inference on these particular tasks? So here, one important thing that I would like to emphasize is that instead of doing this embedding layer, right, so you're also learning the embeddings on the fly for that particular task, you can always use the embeddings that are task agnostic, but these embeddings could be kind of hardwired, like the bag of words or the word to vec or glove. There are different embedding methods, but you can also use a pre-trained embedding that comes out of a particular model. For example, if you look at, we will see what this is as we progress, but this is like a transformer model that basically gives you an embedding uh, for the sentence that we are dealing with, but using a pre-trained neural network. So you just basically give as an input these tokenized representations to obtain a model, and you use that model, the pre-trained BERT model, for in your MLP task. So this is very similar to, for example, using a pre-trained CNN architecture like an Inception or uh, 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 the ImageNet model, and add a few more layers. So here, what we are doing is we are using an embedding that comes from this transformer model, but then you add a few more layers to form your inference. Either it could be a CNN or an MLP model, right? That's the basic idea. So I'm gonna leave this as it is, like to show this show, and the point is like, okay, you can use RNNs also to process one word at a time, but that's the basic message, right? So with that, I think, yeah, I mean, basically I would leave it at that point, but then go to, I think, yeah, one important remark that I would like to make in the context of this neural machine translation, which is again an encoder-decoder architecture. We have seen this before, right? I would like to use this to introduce the attention mechanism, but also introduce one more RNN layer, which is called as a bidirectional RNN layer, which is useful for reading time series, which always need not be processed with causal constraints. So when we say causal, what that means is whenever I'm doing a prediction, I should not see the word that comes next, right? So if you're doing a filling of a word, like fill in the blanks, then it's not sequence. So I can basically look at the fourth word and the second word to fill in the third word. That is fill in the blanks, right? But that is not causal. Causal would mean that to predict the fourth one, I only have information up to time instance 3. I have not seen the fifth instance. That is what RNNs would do. Now, suppose, imagine the following. You would like to use RNNs to do fill in the blanks. Then one way to do that is to incorporate the context information, which is very important, because fill in the blanks, you never know, right? So if you see this 3 examples, so the first, if you want to predict the third word, now the third word, ignoring all this of the simple words, but focusing on what is it, what the main word is, United Kingdom, hearts or bees, that depends on the context. Now, if you would like to see what the context is, then you cannot simply do a sequence prediction like what we have been doing so, but you would also like to see what comes in the future, right? So one way to do this context information, incorporate this context information, is to use something known as a bidirectional RNN, which essentially is two RNNs working in tandem, where the first RNN is looking forward in the time series, the second RNN is looking backwards. Okay, so you basically have two RNNs that go in two directions. That is what is also illustrated in this picture, where you have X1 to process X1, you require input as X0 and maybe H0 that comes as the hidden state, as we know. But the reverse RNN, what it does is it takes X1 as input, but then takes H1, say, let me call it as backward, H1B, and this is the forward, right? So it takes heads the latent information from one step ahead, right? So now the output of that is basically the combination of these two RNNs, right? So what we basically get is, for example, it could be a simple uh, average of the two outputs from these two, or any complicated function of these two. So one is going from left to right, the other one is going from right to left. What does it change in terms of the code that you would write? So instead of using like a simple GRU, like what we were doing before, or an LSTM, you would use this bidirectional word before that. So basically, you are doing two RNNs, and mind you can only do this if you can let go the causality, right? So causality would mean that I am allowed, letting go would mean that I'm allowed to see the future while processing the current input. Okay, in case the applications, you cannot use that. For example, like when you're doing machine translation, right? So if you're doing a text prediction in your Gmail console, you would like to predict what comes next, you cannot use bidirectional RNN. But if you're doing say a translation, you would like to use all the information. So it's not just processing one word at a time. You would also like to process what comes next while processing the current input, right? So that is bidirectional RNN. So this is another model that you would like to know. And this bidirectional RNN, for example, can be right now, what we had seen in this picture is the usual RNN model, where you're basically using only the encoding information in the machine translation. But for example, when you're predicting, say, decoding to a different language, you can basically also use a bidirectional RNN here, right? That is the point. So you already know what is it's not about predicting one sentence, one word at a time, right? It's, although it is sequence modeling, I can take that context information into account while doing predictions. So, and this is common in NLP, unlike time series. Time series, when I'm predicting the future weather, I would not be considering the weather from tomorrow, right? That does not make sense while if I'm predicting today's weather. So if I know that, maybe I can use that to, for example, fill the missing weather information, right? So for example, you see nowadays a lot of these air quality information that is floating around, which is through a bunch of measurements. But oftentimes what happens is that many of these sensors that measure air quality, the sensors might be broken, right? Or some of the faulty sensors. But now you have data from in the future, but now you would like to use that future data that you have measured to fill that missing information, right? So, and then use that to, for instance, predict what comes next, right? So that is where this bidirectionality in general is useful. I hope that is clear. So now let's focus on the attention mechanism. Attention in general is giving a specific weight to the embeddings. Okay, so for example, let's go back to the simple, you can ignore the bidirectionality part and simply assume that, okay, it's a simple RNN taking some inputs and latent space giving you the output. Now, you would like to use the sequence to sequence model here and predict something in the decoder. Okay, so now, for example, I drink milk. Okay, and then actually what you're interested in is making abstraction and making it easy for you to visualize. Suppose this is my input and this is my output, and the intermediate inputs, let's not worry about, or we are not interested in that. So we are only interested in the output that we see here, which is the translation of this, I guess, into French, right? So now when I'm doing the translation, I have three inputs, x0, x1, x2, where the words are tokenized, converted into an embedding, like what we discussed. And then you have the encoder outputs. Now, while decoding, I'm decoding in the same order. So I would be translating I drink milk into a bunch of words, which it's basically a translated version of this. But for instance, when I'm translating, say, the output Y3, recall that it is always an estimate of something related to the, say, in this case, milk. So the point is, when I'm translating milk, that becomes this light, I would like to focus on milk. Although I have these three outputs, which corresponds to outputs from I drink milk, while predicting Y3 prime, I would like to have more focus from the output related to milk, that is Y2. Okay, Y2 is basically taking milk as an input and giving some output in the encoder. So how do we do that? We have to assign weights, and the weights are indicated here by the shades of this black, right? So black, gray, and light gray basically indicates that more this alpha 3, 2, which is basically how much should the encoder encoded output at time 2 depend on output Y3. This is 0 depends on output Y3. That's the basic indexation here. So now you have to have a mechanism that basically tells alpha 32 should be larger. So I'm focusing more on milk, not much on drink and I outputs. Now, that particular idea in general is called as attention. I would like to attend to a particular output more than the other. For example, attention you can also use in graphs, right? So recall that while we were discussing graph neural nets, we were computing embeddings for different nodes. Okay. So now while we are computing embeddings for different nodes, what we are taking into account is the embedding from the neighborhood. I would like to take that into account while computing the embedding for that particular node. Now, within that neighborhood, maybe you would like to give more preference to one of the nodes compared to the other, right? So there could be some stale nodes, but there are more active nodes which you should give more preference to. Now, the question is, how should I automatically compute it, right? So the general idea is attention, but that weight computation, the attention mechanism, is done typically in the following ways. Listening to me for some reason. That resets. Okay, let's see. Okay, so the attention mechanism can be done in the following three ways. One is a simple dot product attention, which basically tells that the weight EI, which will be subsequently normalized, like as we see here, is basically the alignment between HT and YT, right? So I would like to basically see how correlated this is with Y2. Okay, a simple way, no learning parameters involved. So you're basically looking at the similarity between two vectors to compute the attention weight. Okay, and that attention weight is normalized using the softmax operation later on. But the basic idea is you would like to compare two vectors. So how much H2 is aligned to Y1, Y2, or Y0. Okay, now that inner product is going to give you a number. If it is more aligned, then this will be a very high number. So alpha 32 would be more, right? That's the basic idea. The other ways of computing attention, this is non-learnable, non-trainable. There's nothing to train here, right? So you just you have H2 and you have Y2. You compare using this inner product. The other way is to introduce the a trainable matrix. This is trainable. This is trainable matrix where you learn W. Okay, so you basically learn this W to tell, okay, maybe I need to specify for that particular task, how should I measure this correlation, right? So it could be like, I'm taking simply the inner product, but here you're saying that, okay, you're basically telling how should I give preference to each entry in my Y and H vectors, right? So these are different ways of measuring an attention mechanism, measuring attention, or you can also have a tan hyperbolic and more learnable parameters, W and V. So the basic idea is you would like to compare two vectors to arrive at a score. How much should it depend on the other? Okay, so this is generally the attention mechanism. As I told, the attention mechanism can be applied for graphs, text, vision, many other applications. The basic idea is how much should a certain output dominate, or how much should a certain feature dominate the output. That is the basic idea behind attention. So one should attend more than the other. One of the features should be attending more than the other, right? So you can also do this at the input level. For example, you have the feature matrix, which has examples and features. And now what you're basically telling is how much, which feature should basically dominate my next set of features, right? That general principle is called as an attention mechanism. For example, you have this image, and imagine that you're running the goal of this particular exercise that I'll illustrate is to, for example, put a bounding box around this frisbee. Okay, so now if you would like to do that, what are we typically doing? We are correlating running patches. Okay, now you would like to have a mechanism where when you're extracting feature for this particular patch, you give more preference, do that more carefully compared to the other. That is what humans also do, right? So you're looking for frisbee, and then, okay, if there are like many frisbee-like objects, you would focus a bit more on that area. So you would like to focus on that particular feature set. And how do we do that? So you're extracting features, and then for each of the feature that you extract, there is a certain input and output, right? So now if you already know, or if you have a value pair for frisbee, you would use that to see if the feature is more correlated and assign that weight while computing this convolution. Okay, so it need not be limited to text. It can be done for time series. It can be done for graph tasks. It can be done for vision tasks, right? This attention is the a more broader principle that one could use. One more introduction, again, like applicable to all these models, is something known as a skip connection. Skip connection, as the name indicates, you're skipping. And this is also kind of a trick that is used to improve the training, right? Not necessarily related to NLP task, right? But you will see that these are some of the engineering tricks that have been used in transformers. But the idea is the following. Suppose I have say a 2-layer neural network to go from input X to some class labels H of X. That is a task that we're using. Now, suppose during training, okay, you train with a certain binary cross entropy loss, and then you realize that that when you're training, your loss is going down. Okay, so yeah, maybe you start with say 10 power minus 2 and going all the way up to 10 power minus 3. Okay. So now you see that, okay, the loss is decreasing as epochs go and it saturates at some point. But now you're interested in seeing, can this loss go further down? Okay, maybe does it go to 10 power minus 4? Why is it not going? Then what you would do is you would start looking at the weights and biases of each of this layer. So there's W1B1, W2B2. Okay, you start visualizing. Now you see that for some reason, the W1 is not improving. So it is same as what you started with initialization. So whatever, for whatever underlying reason. And because of this, W2 is also not improving as further as it can get, and it is hindering the performance. So because of this reason, people started thinking, how can I not let the learning of layer 2 affect because of whatever is going on in layer 1? So now, if you encounter such problem, what you would try to do is, you would try to bypass this. You would try to bypass that layer if it learns well and good. But in case layer 1 is not learning well, I still would like to proceed with my training. And maybe if I do that, this would go further down. Okay. So that basically is called as a skip connection. And skip connection basically tells that whatever was available to layer 1, it is also available to layer 2. It might not be a simple NLP, but it could be because of all this max pooling and convolutions that you do. So you would like to skip a few layers and not let the error back propagate through those layers to hinder your training. So what you would do is you would add these residual connections, and even though one of the layer fails, you still have a progress in your learning. So that is that idea is called as a skip connection, and often used to speed up training considerably with this. Whenever you see that, okay, it is not one of the layers is not helping you improve the performance or not getting trained at all. Okay, so now with these basic ideas, you have the attention mechanism, you have skip connection. We are now ready. We have the ingredients to discuss what is going on in this. Very popular neural network architecture called transformers. Why is it called a transformer? The basic idea is it looks like the transformer character, right? So I mean, cartoon character, like, okay, it's that that's the basic. I guess the name, but there's no additional meaning associated to that that I can think of to this particular architecture. It appeared in this famous paper called Attention is All You Need, and it has become super popular as an alternative architecture for sequence modeling. Okay. And it is against the basic principle of convolution or affine transformations as we do in CNNs and RNNs, even MLP. So some of the layers are indeed MLPs that we have here, but the basic idea is behind transformers, unlike RNNs, is the following, right? So suppose we have a sequence x1, x2, x3, x4, so x10. So what we typically do in RNNs, although or any sequence modeling that follows the principle of RNNs, for example, AR modeling, moving average models, etc., all assume that there is a sequential dependence. For example, x2 depends on x3, x2, x2 depends on x3, and so on. Although, and through this, we try to propagate the memory sequentially. But transformers basically question this proposition and try to see if x3 can depend on x1 and x2 can depend on x10. That is a more general model, right? So now what that basically means is that any any set of sequence, say with this 10 sliding window of 10, can have any possible dependencies, and we should be able to capture that. So that is the deviation from the principle that was used in RNN, or in bidirectional RNN. Again, like it was something similar to RNN, but in the reverse direction, right? But now the question is, how do we do this? And this is actually what was also being used in databases. So it has a strong connection to what was using in all these database queries, along with uh, 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 sequence models, right? That's how I see as a what transformers is about. So for example, like when we are searching, say something in YouTube, right? So you search for a music or some movie or movie scene in YouTube, you key in a set of words as a query. Okay, now that query is not sequentially tested against the entire database, but how it typically done is that every entry in a database, which is essentially a video, has some value associated with it and some keywords associated with it. Now you do a query. For example, let's look for whatever the new movie is around. So like say you search for that keyword. You don't know what keyword is used to store that movie, but you give as what you would like in English. So you would search like, okay, in the top songs of 2024. Okay, then that is indexed as a particular playlist with certain keywords. Now those two are correlated. So you correlate the query with so-called key, Q and K. You will see these later on. And then subsequently, you will see what is the value of that inner product. You would test against that value. And now you would look at the rank order of that list because of that Q key and value products. And that is what leads to the sorting of the search outputs, right? So this is a classic technique in any database query. And this is what is used in transformers. We will see how that is and how that is used and why is it so relevant. Okay, so yeah, so you can choose a different model, right? But you see that okay, the model is functioning well, but then it could be that okay, some of the layers are not performing well, right? So yeah, you could change a model to see if it drastically improves, but this is another technique to basically use, say, some of the models that are already there, you know that it's performing well, but then, okay, can I speed up the training? So if I skip a few layers which are causing trouble because of either vanishing or gradient issues, can I skip those particular layers but still retain that architecture, right? So oftentimes it could happen that, okay, when you deploy a model, you do an incremental update in your model, and your boss is not allowing to deploy another model because okay, it'll need to undergo all the certification testing, etc. But now can I do a small uh, tweak around that model to still get a better performance, right? That's the idea. Then in that case you could use uh, the skip connection. So it is actually also used in one of the ResNet architectures, right? That's where the res comes from. Um, and and as I told, it need not be applied to vision-based tasks, but as you see, this is also common in the transformer architectures. Yeah, so the attention mechanism, you're basically you're basically telling indeed like posterior to what you have seen in case of the neural translation model, how much, so compare, I have these three outputs with me, and then, okay, I have also started processing these outputs through this latent, the previous time instance outputs through this latent representation. So now the question is, in the decoder, you're feeding an input, right? So for this particular input, which of these three should I select? So having seen this, right? So now alpha is kind of a because after the softmax is indeed like a probabilistic weight that you compute on the fly, posterior to having seen H2. Okay, so what we will do subsequently is yes, the connections are skipped both in the forward and backward pass, right? So okay, so what we will do is I will give you, I'll take you through this architecture to tell what are the components, and then we will go into one block at a time, right? So some of the blocks, I mean, you already know, right? Feed forward is feed forward, linear, softmax. Those things are not going to the details, but what you would see is the following. It is an encoder decoder architecture. What you see here is kind of an encoder, and this is the decoder. Okay, so there are two branches to that. So now inputs are sequences. The input and the output are similar to what goes in an RNN, for instance. Okay, except that you're replacing that RNN box with this complicated box, which is a transformer, to achieve what I was describing here. Okay, now RNN, again, recall, it only depends on the previous input and some memory, right, from the past through this latent state vector H. Now, what we would like to see is that, okay, there could be possible dependence from different inputs. So the input is a sequence up to a certain time. You're looking at a certain time window. Up to that sequence, that is your input. You do a lot of magic, and output is same as what you would like to have for an RNN, a sentiment analysis or a prediction of the next word or fill in the blanks. Okay, so these are the typical things. So now this has two, I would say three main concepts, two of which you have already seen. The first concept is this positional encoding. Okay, this is very important. So we will discuss this. So input text is converted to some embedding. Okay, it could be like a bag of word or a glove or any of the one of the 100 different ways to compute an embedding. That is what gives you a vector. Okay, word converted to a vector. Positional encoding, we'll see what that is. Attention is similar to what we saw, but there is something called as a multi-head attention. We'll see what that is as well. It is repeating the attention many times. Instead of having one attention, you will have like many attentions. That's multi. We will see what that is. And then there is some normalization going on. Feed forward, as you can see, there is kind of a skip connection, right? So there is like a connection going from here to here, here to here, and so on, right? So there are some skip connection layers similar to what we discussed. Now, there is the output of the encoder is fed to the decoder model. Very similar to what was going on in the machine translation, right? So machine translation, there is an input sequence embedding. There is some input from the encoder to the decoder. The decoder is also processing a sequence. Either you can basically not use any of this, or when you start generating the output, you can use that as an input to the next one, right? So you can use the estimate as an input like what we already discussed. Okay, so that architecture is very similar in terms of the input-output relation, except for the system that takes. Again, at the output, the key is masked here. The keyword is masked. You use positional encoding, same architecture, but here it is like on the decoded text, right? So that is what you're processing. there is a masked attention, okay, and then the decoder input and feed forward softmax, right? So the main things that you have to now understand is what is positional encoding, what is masked multi-head and multi-head attentions, right? These are the two important things that we will discuss now, okay? And putting together these things in this particular fashion is the popular transformer architecture. Okay. So now, as I was telling, that I don't want to restrict myself to the ordering in time, which means that T2 is greater than T1, T3 is greater than T2. And in fact, T2 is T1 plus delta T, T3 is T1 plus 2 delta T, right? So this is the assumption which we made use in RNN or any time series processing without explicitly mentioning it, right? That's how the architecture was built, right? That's the recurrence relation that we incorporated. And what does it mean in terms of recurrence relation? This is what it means. Now, what we would like to do is respect this relation, but also say that x3 could depend on x2, but x3 can also depend on x1 more explicitly, while incorporating the positional information where x3 appears, where x1 appears. And that is done via positional encoding. So what positional encoding does is the following. It uses, there are two types of positional encoding. One is either fixed, like what we discussed, or you can learn the positional encoding as well, but we will not discuss that. In the classical positional encoding, a trigonometric function, sine and cosine functions are used to incorporate the temporal information. So the positional encoding itself, you have at different times, you have a vector for positional encoding, and that is added to the input embedding to get the output at the positional encoding. So you have an input, you have an input embedding, and now you generate another vector of the size of the input embedding and add this. Now, how do you generate this? That is through this trigonometric functions, where you say that for every input, the odd positions are cosines of this, and even positions are sines of this, right? So through this formula, you compute this vector. You add that, like what we see here, to get the input to the attention block. Okay. So basically, you're saying what is the location of the word in that sentence. Okay. That is what this positional encoding is trying to do. Okay. So the ith component of the embedding of the word located the pth position in the sentence, right? So that is what this vector would give you. And how we generate this vectors is through the sines and cosines, right? Through orthogonal trigonometric functions. So you're basically telling what is the position of the word in that long sentence through this encoding that is incorporated in the input embedding by a simple addition operation. So now the embedding that comes out at this point is aware of the time index as well, where the position was, what is the position of the word in that sentence. So what we had implicitly assumed, we are making it more explicit through this positional encoding. Okay. Now, I told you about the QKVs and what happens in the databases. Now, the attention mechanism, the way the importance is learned is very similar to what happens in the databases. So we basically learn this QKV matrices. These are trainable matrices. and these are learned as follows. So let's look at how this is learned, right? So suppose we are dealing with this sentence, hi, how are you? Okay. And each of this word has a vector representation. Okay. And that's like this 3-length vector after you do this positional encoding. Now, what we do is for this 4, suppose every sentence has, after padding, has these 4 words. Now I get a matrix, which is Q, which is 3 by 4, and then a query matrix and a key matrix. This is again, as you can see, it is 4 by 3 to generate a score. Okay. So the idea in, say, this YouTube example that I gave, query is something that we key in. Key is the keyword associated to that particular database entry, right? The video that we are looking for, or the set of videos that are there in this YouTube. Now you're looking at correlation, right? So how correlated is the query to the key? So you do this Q times K transpose, which is computing the correlation via these scores. So now, for example, this is giving you the self correlation between the words. And then you have a correlation between, basically relation between how each word is related to the other word. That is self-attention. What you're doing is you're doing a correlation between key and query, right? So how each word is related to every other word, right? So that is what goes in the first row of this, right? High, how high is related to hi, how are you? High is very high. And then, yeah, maybe there's not much going on with the other things, but you see that, for example, how and are kind of having, in this cartoon illustration, very high numbers. So key is basically something that you have for every entry in your database. Query is what I key in, right? A user keys in. That is the basic idea in database. Now, in this particular case, you're basically learning a QK matrix, which is common for all the sentences that you show in the training data set. So in this particular training data, you have sentences that are 4 length long, right? So 4 length long. So the QK is learned. Okay. QK and V are trainable. All these are learned. Now, what you do is once you have a score matrix, you normalize that score depending on how many words you have to get a score matrix, and then you compute a softmax. So that is basically telling you a probabilistic connection between each word in the entry. How is, say, how related to R, right? So what time is it now? So, I mean, for all these examples, you are only before relating the current input to the past with some memory. Now you're computing all possible relations, right? So like this drawing that I was trying to make, you now have through this Q and K, all possible interactions between the words that appear. So you generate a QKV. So how this actually works is as follows. So I have an input. You do X times WQ, X times WK. This is your Q matrix. This is the K matrix. What you basically learn is the WQ and the WK, where X is the output of this positional encoding layer. Okay, so for every input, you multiply, you do an affine transformation with a learnable matrix W, affine transformation with a learnable matrix WK, WQ to get this QKV. And then that is again multiplied with some X times WV, which we call as a value matrix, right? So that is going to give you the output at this particular point. Okay, so now this is basically telling me how words are related in the sentence. So this is completely not related, actually, if you see, to this recurrent autoregressive type of models that we have been seeing so far, but using a slightly different perspective related to this database search, you introduce a trainable parameter, WK, WQ, and WV, to learn this QKV matrices. So once you have this QKV, now you know how much should I attend this value, right? So that is coming through the softmax, right? How much value is again like another matrix. It's a transformation of the input. So here you're telling how each word is related to the other. So you generate a score function and then you test it against a value matrix, right? So that is going to give you the output at this point. Now, this is a single head attention. In a multi-head attention, you have many such QKV matrices. You just don't trust one QKV, but you say, okay, let's do multiple times. And then for each attention, then you concatenate all the outputs and then process that output. So that is what is done in a transformer layer with the experimental evidence that shows that having more attention heads is better than, more expressive than having a single attention head. But each of these attention blocks, what is going on is the same QKV transformation, okay? So is it clear? This is basically the main thing about transformer-based architectures, which is different from the RNN and the CNN architectures, okay? So any questions about this? So if you recollect, this is what is going on in the encoder layer, right? So uh, nothing too complicated except for this positional and multi-head attention. You see the same blocks again in the decoder architecture. The decoder assumes it is taking the output from the encoder, but also it can process the words that you have already predicted and taking that as an input. But as I told, there is one key difference, which is the masked attention layer. So when you're doing sequence prediction, especially at the decoder level, you cannot assume that you know what appears in the past. I mean, what appears in the future. So that means that I'll have to mask. For example, the question is, how are you? And the answer is fine. I'm fine, right? So that is the answer that you would expect from your decoder. So now, when you're computing attentions while decoding, you can only attend to words that appeared in the past and not in the future. So for example, I am fine. So you can attend to, while predicting fine, you can attend to am and I, but while predicting am, I can only attend to I. So that's why we use a masked attention layer, which basically masks the future, right? So because I don't have that information, I cannot use that to compute this Q and K transformation, right? So this QK transpose, I cannot do that. So basically, you only compute for this lower triangular part, which basically has seen the past, right? That is the basic difference between an attention layer and a masked attention layer, right? So you do this for multiple times, and that is the multi-head attention. Okay, the mask is kind of always known, right? So it's like if it's one word prediction or two word prediction, you use the mask appropriately. So that's the difference between a masked multi-head attention. So now you put this together, and the architecture that was using this was the GPT-2. Now we have like newer versions, but the backbone is essentially the same. It is a transformer model, nothing too different. But let me see how this works. Yeah. So I have I did this small exercise. You can also do this if you go to Hugging Face. You can load any model, but nowadays the interface is much more fancier. Just look for Chat GPT, right? So instead of prompting, I'm basically selecting the most appropriate one so that it has some um, uh, past informations from which you can make good predictions. So that people call this prompt engineering, right? So I'm giving a sequence of words here. Today I went to a movie with the hope that basically prompting to show towards a particular sentiment. So Yeah, I mean, whatever it is, right? So you can basically, it starts predicting what in the future. And what it is basically using is the following architecture that I mentioned. Okay. So most of the transformer models that you see are based on the following architecture. But now the question is, okay, I have this architecture. How do I train these Ws and biases that are sitting here, right? So how do I get this QKB matrix? What is the task that I should use to train these models? So to do that, there are two tasks that are typically used. And most of the GPT models that you see are the decoder only models, right? So there is an encoder model and a decoder model. So both these are bidirectional. Bidirectionality, we introduced what that is already, but once you already have this encoding, all you need to do is a decoder, right? So most of the things that you are seeing, a GPT 3.5, GPT-2, GPT-4, etc., are decoder only models, right? Because somebody has already done the training, you just give a query and then processing it gives the output. So the training itself is done on two particular tasks. One is masked language model and next sentence prediction. Masked language model, what that basically means is fill in the blanks. Okay, that's a task. So it is trained on all these tasks. You show a gazillion of documents to these models. And when you have the model, you basically, in the training phase, you mask certain words, like my dog is, okay, what is it, like happy, cute, etc. You mask and you train a predictor to for that particular fill in the blank task, right? So it uses a bidirectional model. So it's processing both from left to right and right to left, and it is predicting what is the output, right? So for all possible things, it's going to give you some probability. The next sentence prediction is basically like what I was showing in the previous demo here, where it was predicting what comes next. So you train on both these tasks to learn all the Q, WK, WV for many heads, as well as the linear layers, etc. Right? So next sentence prediction is like, okay, you start a sentence and then you would like to predict the next output token, right? So yeah, my dog is cute, he likes playing. My dog is cute. How do magnets work, right? So you see that, okay, it should not be the appropriate next sentence that it has to predict. Okay, so the pre-trained models before for training are trained on these two tasks, right? So these two tasks, and what you would basically use is the decoder of that for inference purposes. Okay. Yeah, and in addition, what you could do is, for example, you can use this pre-training what I already mentioned, that you could basically download. Again, if you go to Hugging Face and look for transformers, there are pre-trained models that you can simply download, and then either you use that as an embedding generator in your, say, for example, graph neural network model, or you add a few more layers to do inference on that, right? So that this is what we could potentially use if you have enough memory to load those models, right? That is something that you have to keep in mind. But the earlier versions were not too much of parameter heavy that you could, uh, 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 yeah, I mean, that could still be used in any of the tasks that we would do for practice or any simple applications, right? So usually the simple RNN is an auto-regressive model, which means that it is processing the past input. The bidirectional is basically it is going from left to right as well as left to right. So there are two. BART is at the auto-regressive version, and the BERT is the bidirectional version, but the philosophy is the same. The decoder part is what we actually use. So these have been used along with the retrieval techniques like RAG and prompt engineering to use it not necessarily for text based tasks, but nowadays even for multimodal, which means that you could basically have a GPT type model that processes image, text, time series, speech, all of them together. And I'm sure like many of you have seen these fancy videos that appear once in a while. That okay, it's going to see a video and then help understand what that video is about, give commentary on that, take a PDF and give a summary of that PDF, right? So applications are kind of limitless, but this can also be fine-tuned. For example, for you're now we have no clue on what all data that it has seen for training, but now, for example, I would like to specialize it to some medical purposes. Now you can again fine-tune that more with medical databases and medical prompts to achieve a particular task at hand. For example, chatbots, ticketing systems, uh, and so on, right? So, or even process the social media to detect fake news. Like the example that I was telling, you can use all these models to fine tune it for a particular task at hand, or use it as it is, right? So just show a tweet and then copy the tweet on ChatGPT console and ask like, okay, whether this is true or false, and then maybe it throws some garbage output, maybe it shows some real meaningful output that you expect. So yeah, applications, I guess we all know like e-commerce, yeah, I can use it for content classification, content suggestion, recommendation, and so on. Chatbots, I already mentioned, healthcare for basic uh, conversations. Like, okay, I mean, if you want to get directed to a particular specialization to make an appointment, for instance, right? You just give the initial set of symptoms, and then you don't know which specialist to go to. So that's going to give you a suggestion like, okay, let's make an appointment with the orthopedic or a cardiologist. So that these are some of the tasks that one could think of with these models. Okay, so that's basically what transformers are about, and a super gentle introduction to NLP. As I told, like in the beginning, if you are more interested, then okay, I think yeah, one could basically start with those two books that I mentioned. But if you want to go more in detail, I guess like that would be kind of a module by itself, I would say. To understand different aspects of these transformer architectures, and more about LLMs, how these can be used for generative tasks, and so on. Okay, so that was the that was say basically getting an introduction to the NLP model. So now we have about 20 minutes or so. What I would do is the following, right? So I need about 5 minutes for this. What was it? So the batch normalization. But while I pull up that slides, what I will do is I will let you ask any questions about the module or this particular aspect. So just feel free to unmute your mic and then ask any questions that you might have.
Sir, I have a couple of questions. Can I go
Yes,
ahead?
please. Yeah, please go ahead.
Yeah, I mean, these are more on some of this conceptual thing in CNN, right? See, I mean, in CNN, before, I mean, there are two layers, right? One is CNN, then we feed it to MLP for some decision making. So in CNN, we typically go through multiple layers and in combination with pooling and all. So if the objective of the CNN is to reduce the dimension, right? So why don't we go to pooling directly, right? Like which directly reduces the dimension of the input image and then feed it to MLP. I mean, why convolution has to be done before pooling or something? I can directly go to say either a pooling or maybe through PC or anything where it reduces the dimensionality, right? And then feed it to MLP. I mean, That is
Yeah,
the
yeah.
question.
Yeah. So, see, the goal of CNN is not only reducing the dimension, right? So not using an MLP, but using a CNN. The reason is that I would like to have a network that is scalable irrespective of the size of the input. So for example, I should be able to use a CNN architecture for a 10 megapixel image or a 24 megapixel image. So the CNN architecture should not be should be robust to that change in the input dimension. If I'm directly using an MLP, then I would basically need to change my architecture depending on what is the input that I'm dealing with, right? The size of the input. Now, that is first goal. The second goal is you would still have to learn something. If you're just pooling does not have any learning, right? So you're basically taking a few inputs, combining that, and there's no learning happening there. So what CNN is doing is it is trying to extract information that is relevant for a particular task. And when I say extract information, it is pointwise multiplication with some W variables which you are learning. While pooling is simply taking, okay, you look at a patch, you look at the max entry of that patch. And that max entry of the patch will be a max entry irrespective of the task at hand, right? So, but now with CNN, what you're doing is, or you can take an average pooling, the average will still remain the same, right? But now with CNN, what you're doing is you're taking a weighted average and the weights you're learning. So which pixel should I give more preference and how should I give that preference? That is what you're learning. So similar to what you do in MLP, like X times W, you would like to weigh different features before combining. And how should I weigh? That is what MLP does. So CNN is also doing something similar, but keeping in mind that it makes it scalable.
Yeah, in that case, like I can use pooling itself even before feeding it to CNN, right? So that I am working on a smaller set, reduced set.
Yeah. So, I mean, that mix and match you could do, right? So,
Okay.
I mean, whether I would like to have a CNN pooling, or I can have a pooling CNN, that is,
Got it.
yeah. Mhm. So suppose like, I mean, if I have like a, say 50 megapixel image, right? Which is like super high resolution. And then the task is to differentiate between a cat and a dog. Maybe I don't need such high resolution to do that. So you can, of course, do pooling before.
Yeah, sorry. I have a follow-up question on this.
Sure.
Before I move, before I feed into MLP, like output of the CNN, right? I would have multiple feature maps, right? Multiple small feature maps in a reduced dimension, correct? So when that gets flattened, when that gets vectorized as an input to MLP, since these are multiple, how will, I mean, those are individually vectorized and then learned, or I mean, is there all of them get combined together and then vectorized, or how does that happen?
So yeah, I mean, so that is again a pooling layer, right? So you could either do an average pooling where you vectorize and take an average of all those feature maps, or you select one of those feature maps before the MLP, right? So if it's like a max, then you would just do take a, say, a maximum vector with a maximum energy, or you could take simply a concatenation of all those, or it could be simply an average.
Oh, so that is done by pooling while reading through all these feature maps, is it? That is how
Right. The last layer, okay, you could, I mean, you could either do a concatenation, a max, or an average pooling at that point.
And each of these feature maps are the product of a different filter you would have used.
Correct. Yeah. And each filter would be different, right? So
Different, yeah.
you would learn those filters, and the number of filters would depend on the number of output feature maps that we require and the number of input feature maps that we require.
Got it. Thanks, Percy.
Okay. So Shri, what's...
Yeah, I have 3 questions actually. So the first one is on an unsupervised problem statement we are handling right now. And this question is more around framing the problem statement itself, actually. So we have data set of our share in the market for the last several weeks for different categories and at different levels. And we are building a threat detection system in which we want to flag the records as threat or non-threat for all the competitors that we are having data for. Now, we do not actually have any labels. So we do not have threat versus non-threat label. And we at least want to turn this into a semi-supervised problem where we do build some of the labels. But based on the ecosystem, we know that human intuition would be the worst driver of how to label this. And we want to do it internally through AI and intelligence, right? So assuming that we have the basic dimension of what these competitors are and the last several weeks of numbers, how can we frame this first part of the problem statement where we can at least get to some kind of approximation or semblance of threat by using modeling techniques?
So yeah, in such problems like where annotation or label creation is difficult, okay, but you would like to have an automated way of labeling, or not necessarily using those labels, but you would like to use those labels, which is typically called as a pseudo label, to train a model. So there are two approaches. You would not go unsupervised in this case. There are two ways. One is something called as a self-supervision, self-supervised learning. In self-supervised learning, it's a type of an unsupervised learning where imagine the following, right? So suppose, let me try to create a new slide. Okay. So suppose, imagine the following, right? So I have, say, a data X, right? And now you would like to pass that through some encoder, which is a neural net, and this is going to give you some labels. Okay, this is the typical approach. And now to learn this theta, you need to have true labels against which you can contrast your predicted labels. That is a typical approach. Now, there are two ways to handle your problem. One is you need to generate a label for this so that you can contrast. So one technique that you could use is use something known as a control reference, where this control reference could be a heuristic that you believe is true, right? So for example, in this particular case, you can have, like, say, domain experts who are not looking into each data point, but then there could be some flag generation mechanisms which is automated but naive. But you know that it works. It is not AI ML based, but it is a naive approach saying that, okay, now, say, for example, okay, if the frequency of these transactions are like this, then it will be a threat. So you count basically using simple heuristics or some reference like flag indicators. You have a reference to generate a pseudo label based on X. This is not neural network, but based on experience, you would do that. Now you can use the pseudo label to contrast, generate a loss function. So suppose your true label is yi, pseudo label is pi, and then the hypothesis is f. So now instead of you contrast a loss between pi and f theta. Okay, so that is one way. This is called as a pseudo label using a control. How you can generate this control reference? There can be many ways, right? Based on experience, without individually labeling, it's an automated way. Second approach is what is known as self-supervision, which is again the following. So suppose now imagine the following. I have this data X. Now this data X, I perturb this data X a bit. Okay. Now the goal of this representation, like this embedding generation, like what we also discussed, is that if I have X and delta X, which means that the data points are nearby, the output that I get from these encoders should not be too different. So suppose this is going to give you Z1 and this is going to give you Z2. Now you can use this basically to contrast and learn what is theta. So this will be a function of theta. This will be some g of theta. You can learn this theta. So now what this is going to do is this is going to give you a way to generate the labels or generate the representations without using any human annotated labels. So this is called as self-supervised learning.
Got it. Okay.
So now,
Uh,
okay, now what you can do is now you can use this f of theta to, for example, do a TSNE. Now, this is
yes.
taking into account the in for your particular application, right? So now you could do a TSNE. Now you see that the data points are better clustered than directly applying TSNE on X. The other thing that you could do is suppose in your case, say you have like 1,000,000 data points, but now let's invest a good amount of resource to label, say, 100 or 200 data points using some ethical labeling mechanism. I use like, say, many human annotators who are going to look at one particular data sample. There will be many human annotators to label, right? That's like some robust way of generating, but I cannot scale that approach. So in that particular case, what you can do is you can use this method, which is an unsupervised or a self-supervised method, and then further add a few layers because now you have limited data. Now you can use this to generate, say this could be like H theta or H phi. So you can now with that limited table, you can further train this model to fine tune for a particular task. So
Understood.
ways are usually, so if you look at any method, suppose, so this is my label data. So 20% label, 30% label, and then 80% label. So if you look at any supervised models, the accuracy would go something like this. See, as more label data increases, the accuracy increases. But these two methods that I mentioned, this will be something like this. For any labeled regime, you would like to have a performance that is more or less robust. So these are typical approaches that are available now to handle your situation.
Sure. Thanks, Professor. Next question is regarding large language models.
Hmm.
Once we deploy LLMs, which we connect for various systems, including RAGs and simple prompt engineering, so on and so forth, what are some techniques in model observability and model monitoring to set up a cadence of refresh, fine tuning, or going back to rebuild the model, so on and so forth, for the LLM ops teams?
So when you say model, it is like what do you have in mind?
So, for instance, this is a chatbot in which we have extracted data from one specific system where we already have data points, which is then augmented with some text coming from social media, and then the customer gets to query the chatbot and ask about volume shares, changing perceptions of the customers, and so on, so that there is a central intelligence tool. Now, once we deploy it, we understand that market trends also will shift around, and the LLM efficacy also will probably increase, but not always in the ways that we like. So how can we set up model monitoring? Because we cannot use simple PSI or simple drift metrics. And how do we set up a framework where we know when to retrain, when to refresh, or when to probably change the prompt templates altogether, or like change the retrieval mechanisms?
Yeah, so there's no one concrete way of doing this, right? So this is what is actually referred to as a freshness and an hallucination detector in LLMs. Hallucinating freshness means like, okay, yeah, it's trained on say data set X, but then that becomes like stale as time progresses, but it is not seen, right? So that is typically called as staleness or the freshness detector and the hallucination detector. But hallucination is again like, okay, yeah, it would try to give you some garbage. It like it's supposed to, it has to give some garbage. So
Mm.
there are no robust ways that or more mature ways, let me say, to detect this, because that's one of the limitations of this LLMs. So one way that you could uh, try to incorporate is, again, combining that with traditional approaches like, say, I mean, if you're like, okay, again, thinking of a simple time series type detection problems. So there are these methods called as change detection measures, right? So you would like to measure kind of performance of this eventually from time to time, and then you do something called as a change detector to see how your performance is varying over time, right? And then you would use a threshold on that change detector. So basically, that means that you are evaluating the model on new data, and what you're measuring is the accuracy. You're not retraining the model or redoing any of these RAG prompts, etc., for fine tuning, retraining. So you would basically measure the change detection, and that is a time series. Now, if you expect the change, or if you foresee that the change is too much, then it's a call that you have to make, like whether I have to retrain or not. So it's like post hoc analysis, but yeah, you could use these change detection tools in combination with the models.
Sure, Professor. But I think even that is not industry level mature as we
No,
have
no,
for
it's not. It's
predictive
not.
models.
As I told, like, yeah, I mean, it is. Yeah, I mean, it is a problem. Yeah, freshness and hallucination is a known problem of LLMs. But I mean, yeah, it's a trade-off that you would do, right? So how frequently do I need to retrain, and how to monitor? So monitoring you could do with some kind of a change detector, a change point detector, where you are basically measuring, say, at a certain interval of choice, say every month or every 2 weeks, you are measuring against the new data that you see, and then you would basically compute the accuracy over time window. You see that it is deteriorating, but then the slope at which it is deteriorating, is that acceptable to you or not, right? So it's basically a post hoc time series analysis on the accuracy measure.
Sure, Professor. And the third question is a continuation of this, in fact. So we know that for various predictive modeling problems, there are efficient neural network structures which can be used based on the modality as well as the intent of what we are trying to do for that problem. But due to client pressure, we are having to sell Gen AI as equal to AI. And what it means is we're going for very inefficient modeling structures at times, where just because the data set is maybe a couple of hundred rows, we're asking something like 4O or O1 actually to do reasoning and give us some kind of outputs, right? Now the question is more philosophical, which is how do you see the outlook of LLMs going forward in the next few quarters to years? Where do you see them gaining significant, efficacy and power in dealing with predictive problems as well, not just generative?
So see, I mean, one thing that is kind of straightforward is, like, whenever it is text attributed data, only then LLMs perform well, right? So because that is what it is trained on. And if the data is not text attributed, for example, we are using LLMs for, say, health monitoring of engines. Okay, that is not what it is trained on, but you could train it a bit to analyze such time series as well, and it's going to do well. So in that sense, LLMs are kind of very limited. But for most of the applications that we see, at least in the Indian context, where it is kind of service-oriented tasks that many of us are dealing with text attributed data, that is going to dominate, right? So LLMs are going to dominate, but it's not like it doesn't solve most of the problems, uh, uh, except for these text attributed information that's out there. The other thing is, LLMs are also inference heavy, in the sense that the complexity of LLMs and the latency at inference is very high, and many of the applications cannot afford that inference. So I know half of the companies are still happy using simple models like XGBoost. Many of them are actually happy doing that, even not looking at, say, simple MLP models. They want it simple. They want interpretability and control. Some of them are riding the wave of LLMs, but it is gonna stay, right? So LLMs are very powerful. So I think the next challenges that are while embracing LLMs are to reduce the inference time. I think that is what is important, right? And next to making it more accessible, right? So there are also these efficient LLM models, right, that can be lightweight LLM models. Like, for example, vision, there is a vision transformer or a mobile vision transformer. So these are like lightweight versions of those. So yeah, I think it's gonna stay for more than what you can hope for.
Thank you, Professor.
Okay, so any further questions? Okay, so if not, then one little concept that I mentioned. So why it might be useful for training. So maybe I'll spend like 5 minutes on that, which is called as batch normalization. So recall that if you're using any activation function in any layer, right? So you would not, you can, I mean, this might also be an issue with transformers, but more you don't see transformers training, but you not, so that means you'll also not encounter this. But CNN, MLP, etc., is that while computing the weight update, you want a gradient that is non-zero. So that means step function is not a choice, but many of the functions like sigmoid also has a zero gradient at a certain region. And you would like to avoid that, which means that you will have to stay in this shaded region, which is between 1 and -1. So you want to stay in that region. And that can be easily done at the input when you choose the weights. So what is the output of a neuron? It is like some W transpose X and then a nonlinearity. Now, if I choose weights to be small, normalize the input, then this can the input to the sigmoid activation function can be brought down to this region. But what about the intermediate layers? So to handle that intermediate layer, there is something called as batch normalization. You might have seen what this is, but let me elaborate what that means. So what you typically do is at every layer, you kind of normalize. Similar to how you normalize the input data, you normalize the intermediate outputs as well. So to do that, what you basically do is you compute the mean and the standard deviation from the outputs, and then you normalize that. So doing this, what you're basically doing is you would bring back the data at every layer in this regime. Okay, so oftentimes it's a task that is negligible to uh, uh, compute, but often speeds up the training process, stabilizes the training process, avoids all this gradient issues, and let the network training happen better. So how do we do this? By simply, you've already seen this, I guess, but simply adding this batch normalization there. So the basic idea is that you would basically compute the mean and variance on that mini batch at each layer. So at this output of this layer, you compute batch normalization. Here you compute batch normalization, and then you feed that normalized data as an input. The input data anyway is always normalized, right? So that is what you would do with batch normalization, along with some two trainable parameters to avoid the input to be shrinking too much, right? So normalized input, you don't want that to be shrinking too much. So that's batch normalization. So just thought worthwhile mentioning this. But if you have any questions, we can take it now.
Professor, regarding this batch normalization, in the previous slide, the activation functions were sigmoid and a few others. Does it work with ReLU as well? I mean,
Yeah, so it is in general advisable to, because see, I mean, one thing is saturation, right? So that leads
yeah,
to vanishing gradient. But then if you look at all these ReLU type functions, the
yeah,
other problem that can happen is that the output of this after this activation is super high.
yeah,
And what that means is that the gradient update is dominated by this large value of the gradient.
yeah.
So you don't want to also do that, right? So that's why you try to always normalize, bring it to a scale that is manageable.
Okay.
Yeah, so it's useful for any activation function, not necessarily the sigmoid, right? So for example, in this illustration, you see that it's for this exponential ReLU.
I mean, just like there is the image for sigmoid function on the previous slide, could you please provide for ReLU? I mean, not the other variants of ReLU, but just the ReLU. I mean, where do we want the gradient to be, the range of
So
gradient?
I mean, the gradient, it's always between, say, in this region, right? So something, see, I mean, one simple way to see this is like, if you look at what is going on with a neural network, a multi-layer perceptron is a cascade effect. So now, suppose if I have numbers that are like, say, 0.9 and then a product of 0.9, etc., it should not change too much. But now if I have like a 0.9 and say a point product with a 0.01, etc., the value shrinks.
Okay.
So that is when,
Yeah.
if it shrinks too much, then you will have like, say, WK plus 1 is equal to WK, no update. The other problem that can happen is, suppose I have, say, 10, 100, 100. If these are the numbers that appear in the intermediate layers without normalization, then it is exploding.
Yes.
So now if you remember, say I had this in a simple way, I had something like eta gradient f of x, right? So f of w.
Yeah.
So now this, you would like this to be the update to take into account all the parameters that appear in the gradient, and not just because of the activation function. Now, so suppose these values are, say somewhere around 1 with where you update, and this is about 10 power 5.
Okay. Yeah.
Now that is what would happen with such large numbers when we don't normalize. So
Okay.
you're always interested in being in this region, and that's why, yeah, you scale it down, right? So one way to scale it down is look at the sample mean and the sample variance and bring data somewhere in this region, right?
So it will be 0 to 1 for ReLU.
Yes, yeah.
Okay.
Yeah, when you're using ReLU, I mean, so yeah, because I mean, with ALU and all, it is fine. But if you're using ReLU, then yeah, pushing that to as minus would make
Yeah.
like half the data going to 0, right?
And TANH would also be -1 to 1.
Yes. Yeah. TANH is not, I mean, TANH is very similar to this plot, right? Except for the shift in the axis.
Okay. Thank you. Thank you.
Yeah, so the parameter count for batch normalization, see, I mean, the first 2 steps, there is no parameters at all, okay, that you have to train. But 3 is again a straightforward computation. Epsilon is a parameter that you choose and not train. That is to avoid divide by 0 error, right? So in case sigma b turns out to be close to 0, you don't want to divide it by a very small number. So you don't want to that division to explode the result. Now, it could be that the data is already like between 0 and 1, and then you normalize so that it becomes further small, right? So that you don't want this to be like, say, between -1 and plus 0.1, right? So -0.1 and plus 0.1, you don't want that to be. So, but these 3 steps, it may result that the data further shrinks down to a very small value. So what is done is you introduce some scaling parameters and offset parameters so that this doesn't happen. So in other words, gamma and beta are learnable parameters. So although there are 4 parameters, that is mu, sigma, alpha, beta, only 2 of them are trainable, that is this gamma and beta. Mu and sigma are not trainable. So now if you look at any parameter count here in batch normalization, so it is basically 784 for each of the 784 vector entries. You have 784 times 4 being the number of parameters, that is 3136, but then half of them are not trainable. Out of 4, only 2 of them are trainable. So that's why you see that the number of non-trainable parameters are those many, right? So you do this again, you do plus 1200 by 2. This is by 2 by 2 and then by 2. That's basically the number of non-trainable parameters. The remaining ones are trainable parameters together with these things because of the neural networks, right? So that's how the parameter count evolves. Okay. Okay. So any other questions from the module, or in general, any other questions that you might want to ask? Yeah, so to improve accuracy, right? So one thing that you could do is like what we have seen today, batch normalization, sometimes regularization of the model, sometimes simply playing around with the learning rate of your optimizer, skip connections. Those are the typical ways to make the model a bit more robust and improve accuracy for a given model. Now, the other obvious way is to play around with the network itself. For example, add more layers, more neurons in each layer, change the filter sizes. So these are other ways. And typically, instead of randomly changing, you would do kind of a hyperparameter search over different models and then play around a bit with around those numbers, right? So those are the typical ways to improve accuracy. The other way to improve accuracy is like one common problem that appears in practice is the imbalanced data sets. So for example, think of a binary classification problem and your training data has say 70% from class 1 and 30% from class 0. That is when we say that the data set is imbalanced. And in this particular case, you could, when you're doing binary cross entropy, you are telling that the probability of class 0 and class 1 is half, right? So that's how you weigh the cost function. But now, since that is not true, you do a weighted binary cross entropies, right? So these are typical problems. Class imbalance is a problem that appears normally in practice because, for example, in a medical setting, um, it's common to get data for patients that are unhealthy, because for an obvious reason, if you're healthy, you would not go to a doctor, right? So class imbalance is a common phenomena that appears in many databases, right? Many data sets. For example, like again, health for diagnostics, it is more common that the machines are not faulty. Then you would not design such machines. So data is also dominated by those things, but the minority would be basically the unhealthy or faulty. Okay, the first dense layer, it's basically yeah. So you would basically do 784 times 300 plus 300. Okay, so it is the number of inputs, 784 times the number of neurons plus bias. So this is the size of the W matrix and this is the size of the bias vector. That is the parameter size. Yeah. Okay. So let's see if there are more questions. Okay. So if not, then yeah. So today is more or less the last time that you would see me during these lectures. So I hope the 5 + 1 weeks of whatever we were discussing was little useful, and you would use it hopefully for whatever goals that you had in mind, right? So either just to upskill yourself, or to try out to find a new job, whatever goals you had. All the best with that. I hope this was informative. And I hope to see you maybe at the graduation, or uh, uh, sometime in the future. So with that, I would conclude this lecture. Thank you all for participating in this program, and yeah, learning these things along with us. Thank you all, and all the very best.
Thank you, Professor.
Thank you,
Thank you so much.
Professor.
Thank you.